Good, we have proved now this uniqueness theorem, and this theorem was for one degree of freedom. So I only have one P and I have one Q, and correspondingly I have one U and one V, or the unitary groups. But of course one can think about whether this can be extended to more degrees of freedom. And so I want to make a remark in this direction. So namely kind of the easy remark, if I go over to a finite number of degrees of freedom, and then everything can be extended. And then I want to say that if I go over to infinite degree of freedom, then everything breaks down. And that will be something which will occupy us for the rest of the term, to understand this better. But let me just make the first remark, that if I go from one degree to a finite number of degree, then things are the same. So the theorem and also its proof work in the same way. The theorem and the proof of this uniqueness theorem can be extended, and actually was, I mean, that's yeah, also going back to those old times, so can be extended to a finite number of degrees, let's say n, but n is less than infinity. That's important here. Finite number of degrees of freedom. And maybe I'm just writing down the relations, the CCR and the Weyl relations in this setting, just but not going into details. So the canonical commutation relations in terms of P and Q are now given. I have now not just one P and one Q, but I have n of them. So I have to specify the commutation relations between them. And of course, the important one is the one between the P I and the Q J. But now also not just for the same I and j, but also for different ones. And actually, if I and j are different, then they should also commute. So it should be delta ij, and the only non-commuting issue appears if I is equal to j. And then I have here minus I. Okay, now of course, this I here is not the same I as I'm using here for the indices. So and this is true if I and j are running from 1 up to n. But of course I should now also specify the commutation relations between the p's and the q's. If I only have one p, of course p commutes with itself. But if I have now p1 and p2, I should also have to say what happens with p1 and p2. And there again, I'm assuming that they all commute. So there is everything commutes. The only non-commutivity is between p and q for the same index. So for q, I have qi and qj. This should always be 0, even if, okay, if I is equal to j, of course it's trivial that it is equal to 0, but it should also be equal to 0 if they are different. So this should be like this. Okay, so those are the canonical commutation relations for several degrees of freedom. And of course, again, P and Q are unbounded operators, so one has to deal with domains here. And again, one goes over to the exponentiated unitary groups, for which the P's and the Q's are the generators. And now I have, of course, not just one V and one U group, but I have it for each I and j running from 1 up to n. So the Weyl relations now must also specify the commutation relations between all the V's and the U's. So what are the Weyl relations in this context? Okay, first the U. So for the pi, I'm taking the unitary group. So the ui of t is now e to the I t pi. Okay, I see. I is not a good index here, so maybe I take here a k. Maybe here I should also do the same. K and L, just to avoid this issue that I is now really the square root of -1. So I have here k and L, here k and L for all k and L. So maybe then it's better. In the Weyl relations, I'm taking the UK, so this is e to the I t pk, and I also have the V, let's say the VL of S. This is e to the I s q L. So I'm taking, so the pk is a generator of this unitary group, the ql is a generator of this unitary group. So I mean I have this for all t and s real numbers, and now I have to specify the commutation relations between those guys. And again, now it's not just between a u and a v, but I also have to say what happens between the u's for different indices and the v's for different indices. But of course it is clear, because the generators commute here for different indices, the corresponding groups will also commute. So the Weyl relations are now the u's among themselves, so the UK T and the VL S. Of course this commutes. No, this doesn't, but if I take here the same U, so if I'm taking the U's, so which are the ones for which the generators are the P's. So this here is the PK and this is the PL. Those commute, so the unitary groups also commute. So I have here UL of S, UK of T. And the same for the V's among themselves. So if I have here the VK of T and the VL of S, this also commute. So this is the same as VL of S, VK of T. So this is of course true for all KL and for all S and T. And the only non-trivial relation is again the one between the U and the V. But now again I have the UK of T and the VL of S. And again, because the P and the Q commute, if the indices are different, those guys will also commute. So again I get here just a delta factor, and what I get here is actually a phase, so I'm writing it as e to the I delta KL times S times T, and then I have it the other way around, so VL of S times UK of T. So if k is equal to L, I have here 0, and then I have e to the 0, which is 1. So then they are just commuting, and if k is different from L, then they are commuting, and if k is equal to L, I just get this phase here, which I have in the ordinary Weyl relation for 1 degree of freedom. Then I'm back to what we had before. Good, so that's the Weyl relations. And again, there is a very canonical representation, namely the Schrodinger representation for this finite number of degrees, and this is given as before, but instead of acting on L2 of R, we are acting on L2 of R to the n, and then we just do what we did before for the variable, we do it now for the n different variables which we have. Before we had x, and now we have x1 up to xn. So the Schrodinger representation of those guys is still there, but now of course it's an extension of what we had before, and now we are living on R to the n. So we have functions of n variables, so we can multiply a function with each of the variables, and we can take the derivative of the function with respect to each of the variables. And this will be the different q's and the different p's. So the qj corresponds to the multiplication with the argument xj. If my variables here in R to the n are x1 up to xn, and the pi, maybe again, maybe it's better to call it qk, so this is with respect to xk, and pl, this is taking the derivative with respect to the variable xl. Okay, and of course, if I'm taking the unitary group, so the unitary group for the qk is the multiplication with a unitary phase factor, and unitary group for the p is the shift, but now only the shift in the else variable. Okay, so this all works as before, and in this setting one can prove the same uniqueness theorem, and the proof is also more or less the same as before. So one still has this uniqueness theorem. Of course, on the level of the Weyl relations. So namely, the Weyl relations, okay, we can see he has this decomposition, but let me just say that each irreducible representation is equivalent to this Schrodinger representation. So each irreducible representation of the Weyl relations is unitarily equivalent to the Schrodinger representation. Good. Okay, so this is the finite number of degrees of freedom, and of course one might ask what happens if I have infinitely many. So instead of just having a finite number of p's or q's, I can consider an infinite number. And this is something which in quantum field theory, for example, really plays a role and what you want to do. So this is really important in physics. And you might wonder, okay, first guess would be then it should still be true, maybe. But if you're looking on the proof, you see that the proof which we gave in one dimension and which also works in finite dimensions does not work anymore in the infinite case. So at least, yeah, so the second part of this remark is now going over to an infinite number of degrees of freedom. And then one first sees that the proof breaks down. The proof breaks down in this situation. And the reason is, in particular, that I don't have a Gaussian measure on R to infinity. So I mean, we took this kernel, this h, e to the minus 1 over 4 x squared plus y squared, and we used this kernel to integrating over our Weyl operators. But if you want to do this in infinite dimensions, this doesn't make sense anymore. You cannot make any sense out of this. In particular, this means there is no Gaussian measure on R to infinity. So e to the minus x squared, this gives you the Gaussian measure in R, and you have the corresponding Gaussian measure on R to the n. But on R to infinity, there is no analog of this. So this doesn't work, and you cannot use this. Okay, but you might think, okay, maybe the proof breaks down, but the theorem is still okay. But this is absolutely not the case. So it's really that it's not just the proof doesn't work anymore, but the theorem is really wrong, and it's really totally wrong. So the theorem does not hold anymore. Okay, and this is really a big thing which we want to understand. So the rest of the term essentially will be to get an idea what is going on in infinite dimensions. So the situation there is very different from the finite case, and there are actually, there are a huge amount of irreducible representations of the CCR in infinite dimensions. And we will try to get at least some idea and understanding of this. So the last part of the course will really address the situation, what happens here. But it will be very different from here. Good. Okay, that's it for now, and then next year we go infinite.